Lesson 5, Linear and Binary Searching. In this video, we present two ways to search an array for a target element, linear and binary search. For the binary search, we will need the elements of the array to be sorted like this, while the linear search will always work even when the elements of an array are not sorted. We begin the linear search algorithm with an array of elements and a target element that we want to find in the array. Starting at the first element, we begin checking each element for equality until we find the element or fail to find it and reach the end of the array. Here's the pseudocode for the linear search function. The function takes three arguments: an array, its size, and the target element that we are searching for. The algorithm consists of a single loop which runs over the elements of the array and checks each to see whether it is equal to the target. If so, the index is returned. Otherwise, -1 is returned to indicate that the element is not in the array. So how fast is the linear search? In the best case, we could find the target at the first index and we would only need one comparison. In the worst case, the element could be at the end of the array and would require n comparisons to find it if the array is of length n. Assuming that the target has an equally likely chance of being at any index in the array, then the average number of tests performed will be n+1/2. Generally, we will be most concerned with how an algorithm performs on average. If the array is sorted, we can use the binary search to find the target element much faster. We start the binary search by checking the middle element to see if it is larger than the target. If it is, we can eliminate the last half of the array as possibilities. If the middle element is less than or equal to the target, then we can eliminate the first half of the array. By repeatedly making such comparisons, we continue to eliminate half of the remaining entries until only one is left, and we check that one for equality. To further illustrate this, we give an example of the binary search algorithm in action. We begin with this sorted array of integers and a target value of 14. First, we compare the target to the middle or approximately middle element. In this case, we check to see whether 14 is less than 25. Since it is, we know that the target value 14 cannot be in the last half of the array, so we gray that out for illustration. The first four elements are the only viable possibilities now, so we compare the target to the middle element of those. In this case, we test to see whether 14 is less than 14. Since it isn't, we know that 14 isn't in the first two entries of the array. Notice that even though we are comparing the target to the element of the same value, we did not do an equality check, so the algorithm does not know at this point that the target value is in the third element. With just the third and fourth elements left as possibilities, we test the target against the middle value again. Our middle is always the larger of the two for an even set. Here, we test whether the target is less than 15. Since it is, we can eliminate that element. With only one element left, we test whether it is equal to the target and see that we have found our element. Our algorithm for the binary search requires approximately log base 2 of n+1 comparisons for the best, worst, and average cases. As we stated before, the important time is the average time, so the binary search is much faster on average than the linear search. For comparison, consider an array of 100 elements. The average number of comparisons in this case for the linear search is 50.5, while the average number of comparisons for the binary search is 7.72. For 1,000 elements, we have 500.5 comparisons for linear search and 10.976 comparisons for binary search. Note that it is possible to improve our best case search for the binary search by checking for equality at each stage as well as inequality. In this case, we might be able to stop the search at our first check if we find the element. However, this requires 2 checks at each stage and slows down the algorithm on average. Here's the pseudocode for the binary search function. Like the linear search, the function takes an array, its size, and the target as parameters. For the algorithm, we keep a low and high index which bound the set of viable entries, with low being the least viable index and high being the index of the first entry that is not viable. Initially, we set low and high to 0 and the size of the array respectively. Then we run a while loop until the viable set has only one element. The while loop repeatedly takes the average of low and high as a test value. If the test value is higher than the target, we set high to the test value. Otherwise, we set low to the test value. This keeps the viable set bracketed. Once the while loop exits, we have only one viable entry at low. So we test it for equality and return low if it is the target. Otherwise, we return -1 to indicate that the target isn't in the array. There are two additional circumstances to consider: missing and multiple elements. If there are multiple copies of the target in the array, both searches will only find one instance. If the target is not in the array, the linear search will require n comparisons, and the binary search will require approximately log base 2 of n plus 1 comparisons. The C++ code for the linear and binary search algorithms is available on our website at zoax.net, as well as some further analysis of the algorithms. This concludes the lesson.